Hey everybody, this is my second chapter 10 video. This one's on 10.2, and 10.2 is a difference of means. So a sampling distribution, confidence intervals, and hypothesis testing for a difference of two means. I'm going to kind of flip back and forth between the homework quiz and the notes. So I left these guided notes in Google Classroom, but these are the filled-in version. And I mentioned how Chapter 10 isn't much different than Chapter 9, except for now we're dealing with two means instead of one. And the difference being condition-wise, really sampling distribution-wise, is now I have two samples, and the mean of that sampling distribution is the difference of the means. So if I subtract these two distributions, the mean is going to be the difference. And it's normal if the sample sizes are big enough. Up the center, the mean 1 minus mean 2 will give you the center, and the spread or the standard deviation is the sum of the variances over the sample sizes. And that goes all the way back to combining random variables, where when we found the new standard deviation, if you added or subtracted random variables, we always added the variances and then took the square root. So same idea here. I think that's what this first question is going to ask us about. So in a study of heart surgery, one issue was the effect of drugs called beta blockers on pulse rate. The available subjects were divided into two groups of 30. I got two groups of 30 each. One group received a beta blocker, the other group received a placebo. The pulse rate of each patient at a critical point during the operation was recorded. The treatment group had a mean pulse rate of 65.2 and a standard deviation of 7.8. And the control group had a mean pulse rate of 70.3 and a standard deviation of 8.3. They want us to find the standard error for the difference in mean pulse rates between the two groups. So standard error is just another term for saying the standard deviation of the sampling distribution. So keep in mind, both of these have their own standard deviations. But now that I'm making it a sampling distribution of all possible samples the same size, for the difference of these means, I need to do a little bit different of a formula for standard deviation using these. And that formula we just looked at here, it's going to be the sum of the variances over the sample size, and then take the square root. So for my new standard deviation, and notation's important. So here my standard deviation, let me go back to my notes real quick. Notice I have sigma 1 and n1. That's come from the first sample. So here that'll be our treatment group. And then sigma 2, n2, that's our control group. So I'm going to calculate this. My new standard deviation, or my standard error, of mu1 minus mu2. That's going to be the square root, the variances, so 7.8 squared over that sample size was 30, plus the other one was 8.3 squared over 30. And if you do that in the calculator, you get 2.080. And then if I move on to the next part, construct and interpret a 99% confidence interval for the difference in mean pulse rates. Let me go back to my notes again. So confidence interval formula are very similar. It's just now I have a difference of two means. I have T star just like before, and my standard error is a little bit different because I have a sum, again, a difference of means, and I'm adding the variances divided by their sample size. So same process. There's also a calculator shortcut. I'll do it both ways here, and then we'll probably stick with the shortcut. So construct and interpret a 99% confidence interval. Let's first check our conditions. So random. Again, you have to write this out. I'm just going to write R because I'm writing with my finger. So random, they said they randomly assigned the groups, so that's enough for us for random. Normal. It's the same normal condition as last chapter, but now you have to check it twice. So you're like Santa Claus. You make a list, check it twice. So we're like Santa. We have our conditions. We check them twice. So normal, both sample sizes, so N1 was greater than was 30, at least 30. And then 2 was at least 30. So those are large enough to say that that normal condition's met. And then last, independent, again, I got to check it twice. Is 30 patients in each group less than all possible patients that are receiving these beta blockers or not during surgeries? Sure, we'll say yes, there's a lot more than 300 surgeries for this heart surgery. And then if I want to do this the long way, so notice the formula is now a difference of means, difference of sample means. And then plus or minus T star. And then times the square root of, we already found this in the previous part. And really, we found this, we found the standard error. The difference in the means is just simply subtracting the means above. So it's going to be 65.2 minus 70.3. That's going to give me a new mean of, I believe, negative 5.1. And then T star, do a little bit of work. I'm going to pause this and open my calculator. All right, I opened my calculator up, and I'm calculating T star. So if 99% confidence, and I want a left tail, that means there's 1% left over, so 0.5% in each tail. So I did an inverse T of 0.005, that's 0.5%, and I left my degrees of freedom of 29. So similar to with proportions, a responsible degrees of freedom here would be n-1 of the smaller of the sample sizes. Well, these are both size 30, so 29 is our degrees of freedom. And there is my best estimate at T star. So 2.76. And we just found the 2.080. That's a 2. And if you calculate that, you get a confidence interval where the lower limit's negative 10.8. And it goes up to 0.6. And now the same calculator shortcut I could do with proportions, I could do with means. So here I go back to my calculator. I can go to Menu, Statistics, Confidence Intervals, and this is going to be a 2-sample T interval. We have statistics. So I'm going to hit this arrow and go to Stats. And our mean one was, let me look back again, 65.2. Our standard deviation was 7.8. That sample size was 30. And then the other group, the mean pulse rate was 70.3. Standard deviation was 8.3. And then the sample size was again 30. We want a 0.99 confidence level. And then just leave this where it says pool. Just leave it as no. Never change that to yes. And I click OK. And this interval comes up as negative 10.6 to 0.44. Or to 0.4 if you went around to one place. So the calculator method. And I would just report everything that came out on that screen, aside what I typed in. So really my interval itself, my difference, that was the two means subtracted, my margin of error, my degrees of freedom. I mean, I would just write everything in that blue box down on the exam if I was using my calculator. And the difference in the interval makes it slightly different than the other calculation is really this degrees of freedom and the margin of error, the rounding we used in our T star and the rounding we used in our standard error. That's what caused this interval to be slightly off. It would be correct on an AP exam regardless. So negative 10.6, I think it was 0.4. So we'd conclude here we are 99% confident the true mean difference in pulse rates for each of these treatment groups was between negative 10.6 and 0.4 beats. Same situation, but now I'm going to do a hypothesis test to see if beta blockers reduce mean pulse rate. So let's think about what this means. Reduce. That means if I subtract them, it's going to make that difference less than 0. So we're going to assume here that if I subtract them, it's going to equal 0. And that means the alternative is we're going to subtract them and say it's less than 0. So my null hypothesis here, we're going to say that the mean with the beta blockers or the mean of the treatment group, minus the mean of the control group, we're going to say that equals 0. And then alternatively, we're going to say the mean of the treatment group minus the mean of the control group. Oh, we don't want an equal to, sorry. We want that to be less than 0. We want to reduce the pulse rate. And then we need to define the parameters. So here you'd say mu t is the mean treatment group, or the mean pulse rate of the treatment group. Sorry, I'm writing with my finger. So mean pulse rate of the treatment group. And mu c is the mean pulse rate of the control group. And you could name it mu1 and mu2, that's perfectly fine. As long as you define what they mean in words or what they're representing. D, the test statistic, t equal to negative 2.453. Determine the p-value and draw an appropriate conclusion using the 0.5 level. So let's see what this means. So they calculated the t for us. So remember, we have the sampling distribution that, I want to say it's normal, but it's a t distribution, right? It looks normal. The mean of a standard t is 0. And we want to know, well, the t statistic that was calculated, almost like a z-score, a t-score, was over here at negative 2 point something, 2.453. Well, what a hypothesis test does is it calculates that value. So if I do that with a norm CDF, or sorry, not norm CDF, t-CDF, that's my lower bound, negative 2.453, I believe. Yep. And my degrees of freedom here, we'll do the conservative 29. And I get this p-value of 0.010, which means that's the area in here. And I'm going to show you the other way. So you could have done a test in the calculator. So I could have went all the way to the whole test myself. Menu, statistics, oops, stat tests. We're doing a 2-sample t-test. We have statistics. Same thing we entered before. 65.2, 7.8, 30, 70.3, 8.3, 30. And we're going to do less than. And here I get a p-value of 0.009, but notice the rounding was different in the t-statistic. So either one, again, is acceptable. If you went back into the full test and you said the p-value is 0.009, that's close enough to this 0.010, because in either case, we're going to make the same decision based on that alpha. So based on that alpha, because our p-value, however you calculated it, is less than 0.05, we're going to reject the null hypothesis. Meaning we're going to conclude that these beta blockers are reducing mean pulse rate, or we'd say we have sufficient evidence that these beta blockers are going to reduce mean pulse rate. And that is it. I will see you guys Tuesday, Wednesday, Thursday for some practice FRQs.